Hello and welcome to the webinar titled A Healthcare Evolution, Modernizing Your Health Plan with an AI Operating System, presented by Machinify and Fierce Healthcare. My name is Janelle Carri Moto and I'll be moderating this webinar. Before we get started, here are a few housekeeping notes. To learn more about our speaker, please visit the speaker bio window. Additional resources are available in the handouts window, and if you close one of the windows and need to reopen it, click the name in the top navigation bar. This webinar is being recorded and will be available on demand within 24 hours. And finally, I will be moderating a live Q&A session after the presentation. If you have any questions for our speaker, you can enter them anytime in the Submit Questions window. I am now pleased to introduce Prasanna Ganesan, Chief Product Officer at Machinify. Prasanna, the floor is yours.
I've been a technologist for 20 years. I graduated with a PhD in computer science nearby here at Stanford. And I've been in Silicon Valley ever since, building a series of technology companies, trying to bring industries, modernize industries with cutting edge tech. And for the last 10 years, I've been working in the world of machine learning and AI, specifically applied to the world of healthcare, looking at ways in which we can increase efficiencies and increase the accuracy of decision making through the use of data to learn about the right things to do. Today, we want to talk about this idea of an AI operating system. I feel like over the last couple of years, we've been living through a pretty large phase shift in how technology is evolving. With large language models, we've seen pretty dramatic improvements and really changes in what machines are good at. And that's created a lot of new opportunities for us to rethink how traditional processes have run, what's the division of labor between human and machine. And so it's kind of a great time to be alive and innovating on how we can find new solutions to age-old problems. So the agenda for the conversation today, we'll probably spend about 40 minutes walking through this and reserve a fair amount of time for Q&A. We want to talk about what does it really mean to build AI. In particular, the focus of this talk is around using AI in production, not just to run experiments and prove that something could theoretically work, but the practical challenges that come with incorporating AI in day-to-day production processes. So our perspective on that is that there's a fair amount of infrastructure, surrounding infrastructure and machinery that's needed to be able to incorporate it successfully in production. And part of the talk today is going to be about explaining why we need that and how we would structure underlying support infrastructure to be able to be successful in seeing business impact and to be able to scale out the use of AI across a series of use cases within the enterprise. Let's maybe start by talking about the difference between experimental and operational AI. So normally how we get exposed to an AI project is under the thesis that maybe we have vendors who come in, or maybe you read about what AI can do on the internet, and we say, hey, how about we try applying AI to a particular problem that we have? Maybe it's a problem where machines have historically been good. It's an analytical problem where maybe you need to rank some set of things and there's lots of signals and you want to use machine learning to do that. Or it may be something where there's a task to be automated and maybe humans are doing the task today and we think that, it may be time that machines can actually do it almost as well. In both of those cases, really the mindset that we go into those projects with is really one of experimentation, where we're hoping to discover that a solution with technology can actually compete with the artisanal solution, which may be that a human expert's doing the job, or it may be that there's a set of rules that people have crafted that's doing the job. And the focus in these sessions tends to be more on, will the AI work at all? And the reality, in fact, is that, there may be many tasks for which AI is unsuited, so that it may fail. And so the focus is very much on, can it go right, even in some constrained set of circumstances? And you try to add more and more constraints. So let's focus on a narrow subset of the problem. Let's focus on only focusing on certain diagnosis codes or certain lines of business or whatever the case may be, certain markets, certain types of situations, to carve out a narrow enough problem where we can convince ourselves that there is some promise that we can actually build a solution that could work. And usually you're also doing it with static data, historical data maybe. You're not really looking to solve for all the complexities of the real world. You're trying to establish proof that something could work. And this is a very important first step in validating a use case, in declaring that, in fact, it is worthy of, or it is capable of being transformed. But it's very much an optimist view of the world. Like, it's a glass half full view of the world, where we're really punting on all the other kinds of problems that exist that we need to deal with if we were to ever put it in production. As an analogy, I remember back in, I think it was 2009, you drive around Mountain View, California, and you saw self-driving cars from Google driving around, Toyota Priuses in those days. And that was a great example of experimental AI. Impressively, it actually did not have drivers even then, or there were tiny versions of those cars which didn't have drivers. And it's now 2025, and you can finally see Waymos on the street in San Francisco. That's an example of real operational AI. And it took almost 17 years in between to go from something that could work in some limited situations to something that could actually work at scale. Now, self-driving cars, notoriously hard problem. You can kill a lot of people if, even if you fail 1% of the time. In healthcare administration, the bar is a little bit lower, but in the provision of care, you have very analogous problems where there's a lot of problems to solve to go from this experimental world to a world of operations where you don't no longer just ask, can it work, but really, will it work in every single situation? So what are the challenges that come with that? As soon as you scale anything, you're going to have to deal with a lot more corner cases than you could get away with in an experimental setting. You have hundreds of thousands of medical procedures and diagnoses to the extent that you're building out an AI solution that works for a handful of them, but doesn't really work for the rest, or works less well for the rest. You have to start asking yourself questions about how do I know? Does it work well for the tail, or does it only work for the common case? How would I even discover where it works and where it doesn't work? How would I put in place a program to know how to use it safely? How do I put guardrails? Maybe I could still use it where it works well and not use it where it doesn't, but how would I track that? So all of these become real problems that we have to confront before we can deploy solutions in production. And most of it comes down to various frameworks that we need for gathering visibility on what's working, what's not working, how to react to it, and how to ensure safe deployment. And we will cover a lot of what goes on there. The other key element is you need a tight data integration. Quite often in the world of running a proof of concept, it's easy to fall into a trap of thinking it's all going to work. I mean, it's easy to gather some historical data and build out something. But in real life, data arrives in different patterns. You may not have the freshest data. You can have the smartest AI in the world, but it operates on the wrong data. You will get to the wrong answer. So you have a lot of software engineering burdens on making sure that the flow of data is accurate, that we're operating on the freshest possible knowledge, that we're making the right decisions on the right information. And those tend to go wrong quite a lot, especially in healthcare, where healthcare IT is always a constraint. We are dealing with a lot of legacy systems, and the nature and the maturity of the integrations can have significant impacts on the quality of business results seen. And that's what we're going to talk about. How do we successfully operationalize AI? A few examples where, just to make sure that this doesn't sound like science fiction, AI is operational today in lots of settings, even within healthcare. I think claims processing has been one of the earliest places where it's taken off, thanks to the fact that it's much less risky to use AI in those settings relative to, let's say, the provision of care, where the challenges are much more significant. And even within the world of claims processing, we've seen AI, we've successfully used AI across the board for many different kinds of interventions, all the way from solving eligibility problems to being able to figure out payment rules to being able to do clinical analysis of claims. So what are the different kinds of, if you want to bucket the types of challenges that we have in operationalizing AI, I would say there are 5 buckets. The first challenge always ends up being, how do you get your hands on the right data? If you think about optimizing a business process or identifying some element in the process and automating it, in order for us to know whether something's going to work or not, in order for us to put metrics in place, we end up needing data to know how well the process is functioning today. And to the extent we intervene, we want to gather data on how well it will function going forward. And the underlying data is almost never sitting in one place. There are multiple systems that may have information that we need. We may need to bring it together even to train a model to know what is the right thing to do. And we certainly need the data to be flowing continuously in order to know whether the intervention is successful. This often ends up being a pretty significant hurdle that is meaningful investment needed. And when we try to cheap out on those investments, we can actually end up affecting the quality of the output. For example, you could get a stale copy of data, which may be a lot easier to get a data dump once a month than it is to get data in real time. But to the extent that changes to that data end up affecting the quality of decision making, it can have material impact on the benefit that we measure or the cost that we incur by making the wrong decisions. So building the right data integrations and exercising good judgment on which data we must really invest in getting the highest quality version of and which data we can maybe get away with lower quality versions becomes really important. The second major challenge that we usually see is that reducing AI into a business process is usually not a plug and play solution. There is an existing workflow for executing a process. No matter what process you think about, there's a series of steps in a flowchart. There are possibly people doing those steps, or maybe there's a rules-based software system that's executing those steps. And as we think about introducing AI to optimize the process, it is the first baby steps may involve taking one of the elements in that flowchart and saying, okay, let's have AI do that step, or let's have AI do a first version that a human can then review and correct. But what usually inevitably ends up happening is that as the AI gets more mature, we realize, oh, we need to redesign the workflow. And to the extent there are existing workflow systems, it becomes quite challenging to integrate with those workflow systems and execute the change management needed to be able to change those workflows. And that can often be a limiter of how much value gets transmitted. Increasingly, what we're seeing, especially with the advances in how fast software is starting to get built with modern AI, is that over a period of a year or two, once you start introducing AI into a process, you inevitably end up figuring out how to rip out the entire workflow and replace the workflow. And thankfully, with software development getting cheaper, it becomes possible to build out new solutions for these areas. But inevitably, that's an essential element of maximizing value. You cannot just substitute out AI for a human in an existing workflow. We have to really reimagine what the workflow looks like. What's the partnership between human and machine to execute the workflow in the most effective way going forward? A third piece of the puzzle is ROI. Like, how do you measure ROI? How do you ensure that you have a phased approach where we are seeing ourselves succeed and then doubling down and creating more and more success? The ROI challenge, and there are a couple of different vectors through which usually you see returns from AI. The first vector is around quality of decision making. There are certain areas where, let's say, you're looking at payment integrity. A common measure of quality of decision making may be something like a hit rate. If you were to stop a claim, what fraction of the time are you actually right in doing so? Do we maximize the odds that the claim is wrong every time we stop it? That kind of ROI usually tends to be easier to measure, quicker to measure. We know the basic hit rate before the intervention. You introduce some AI, you can measure, did the hit rate improve, did it not improve? So that's relatively quick to measure. But when it comes to ROI, which is around productivity, especially if it involves workflow redesign, it's usually a longer process to measure. And even instrumenting systems to measure it correctly can take a meaningful amount of time. And decoupling all the different things that are changing at the same time can be quite challenging. We've certainly gone through exercises where we thought, hey, we introduced this new solution. We thought it would increase productivity. It didn't appear to. But then at the same time, maybe your hit rate is going up and correcting claims takes longer than declaring that claims have nothing wrong with them. So it can actually bias your productivity measurements if you're uncareful. So it takes a fair bit of effort to instrument systems correctly so that we are measuring the right variables that are correlated to business value. And we can track that we're improving those metrics on a week by week or month by month basis. A key element of proving ROI is that we need programs that allow us to iterate, create visibility, identify what's working, what's not working, and have a means by which you identify the thing that's not working, and you can work on it and show that it's improving. So creating all the observability around where is the place that's working and where is the place that's not is a really, really key element with operationalization. Obviously, there are infrastructure needs that we have. It's become significantly easier in the cloud to be able to deploy AI, and I guess the cloud is more or less the default choice now for deploying any kind of AI solution. But with the underlying model providers and the models themselves evolving really rapidly, every 2 months you have a new king of models that's getting announced. And if we want to keep up with the latest and greatest advancements in the state of AI, it requires us to be extremely nimble on the infrastructure side and being able to shift demand to the right suppliers of foundation models and to incorporate all the necessary testing and needed in order to be able to be so nimble in making different choices. And finally, the last piece, which is actually really important, is you end up needing a set of domain experts whose primary job is to validate that the solution is being implemented well and that it's continuously improving. And those domain experts aren't just technologists or data scientists or machine learning engineers. They actually have to be subject matter experts who are extremely strong in process design and can speak authoritatively to what is the right thing to do. A lot of the jobs that we look to introduce AI into our workflows, we look to introduce AI into, in order for us to measure whether it's doing the right thing or the wrong thing, we need a clear standard for what is done. And in many of these functions, that standard isn't pre-written. If you say what is the right way to diagnose a patient with a condition, that's not necessarily an objective standard that's trivial to explain in 60 seconds to a technologist. It's actually a very nuanced, complicated decision. And really, the only real way to measure whether AI is doing something right or wrong is to get very fine-grained feedback from a human expert to understand what it's doing right and what it's not, so that we can build a feedback loop where it gets better. And those domain experts are relatively hard to find. They're constantly in demand, and to dedicate their time to actually improving the core technology can sometimes be quite challenging. So those are the 5 big areas that we see where we need to invest in order to maximize odds of success of a project. Now let's get into the idea of an AI operating system. Double click on the word operating system, and I'm going to use a layman's explanation of what an operating system is, drawing the analogy to the world of computers. You've got lots of, historically, we had a lot of computer hardware, and the idea of an operating system came about in order to standardize how software could interact with the underlying hardware. As a naive model of a computer, you have a keyboard, you have a screen, you have a disk. And if I were writing a word processing application, clearly I need to capture inputs that the user is typing on the keyboard. I need to make it appear on the screen. I need to store the document on a disk. And in the absence of an operating system, I, as an application developer, would have to figure out how the specifics of that work relative to each keyboard manufacturer or maker of a computer monitor or a maker of a hard disk, which would have made it completely unscalable. Because you would have, and then if I then built a different application, a spreadsheet, I'd have to figure all of that out all over again. The job of the operating system is to standardize how applications can access core functionality that should be universally available to be able to solve their problems. So the maker of the application could focus on their layer of the stack and could rely upon the operating system to provide it with all the necessary building blocks that makes it easy to build an application. Now, when we think about using AI in healthcare, we have an analogous need. There is a set of core primitives that every application needs that we want to provide as a common set of building blocks that makes it easy to do the net new intervention. Now, if we go deeper on that, what are those building blocks? The number one idea here is that most interventions in healthcare will end up relying on the same underlying set of data. So if you think about the payer side of the universe, what are the key data sets in healthcare? You've got claims, you've got medical records, you've got provider contracts, and then you've got all the information that constitute the rules of the game, which would be policies of various kinds and provider manuals and things like that. And armed with those data sets and the insights derived from those data sets, we should be able to solve a wide variety of problems. Like most claims processing workflows will end up relying on the same data sets for irrespective of the exact nature of the problem that you're looking to automate. Whether it's a coordination of benefits problem or a subrogation problem or a payment accuracy problem, all of those ultimately can be traced down. If you thought about, okay, how do I solve it? It can be traced down to data that lives in that common data layer. So to the extent that you can build a core data foundation that exposes the patterns of error that are occurring and provides operational live access to the data so you can make smarter decisions about how to pay things, that investment ends up being reusable across a wide variety of applications. Now, you can take that one step, a few steps, 3 steps further really here, where it's not just the raw data. You can start imagining that you can build additional building blocks above and beyond the data, but founded upon it, which makes it easier and easier to roll out net new interventions of various kinds. So let's take a look at what some of those can be. We talked about the lowest level of data. So that's like your claims and your policies and your medical records. The next layer above that would be a series of foundation models. So it turns out, and really this is the key insight behind the growth of LLMs that we've seen. It turns out that if you take a large pile of data and you start teaching machines, so long as you have extremely high volumes of data, let's say billions of claims, tens of billions of claims even, you can start teaching machines to reason about what tends to happen. You can essentially find emergent patterns in the data and teach machines the fundamentals of the underlying processes that drive the creation of the data. An example would be if you look at the sequence of claims that any given patient is associated with any given patient, and you start looking at billions of such sequences of encounters, or hundreds of millions at least, you can start teaching machines patterns where they can start guessing what tends to come after what. If a patient has a certain set of conditions, they get a certain set of treatments, what are the next set of conditions that they're likely to be diagnosed with, what are the next set of treatments they're likely to need. So that's a thing that machines can learn, like models can learn, given exposure to enough sequences of such claims. Similarly, if you go look at the sequences of claims built by a provider, you can learn patterns about what comes next. If you expose models to medical records, right, all the different ways in which a doctor might be, all the different situations in which different doctors might be diagnosing the same condition, you can start to learn patterns of, what kinds of lab results and signs and symptoms and vitals tend to result in what kinds of diagnoses. So those are what we consider to be foundation models. So foundation models are interesting in that they aren't tailored to just solve a very specific business problem. They're really absorbing the fundamentals of how healthcare works, whether that's at the billing side with claims, whether that's in the medical diagnosis side from medical records, or hybrid and payment models. If you go read every contract that's written between provider and payer, you start to learn how contracts are structured for different kinds of encounters. So that gives us a fairly core set of fundamental building blocks, which then end up being useful in a variety of different settings. That's what makes them foundation models. These foundation models are fairly expensive to build, and the cost of building them does need to be amortized across a number of different applications that can reuse the same models. Then the layer above that is where you start focusing on specific tasks that are tied to very specific settings where we want to intervene at the business level. And the task isn't the same as a function. It's really a breakdown of one element of a function. An example could be, an example of a task could be to decide whether a claim is likely to be suspect in the way it's been coded for a particular scenario. Maybe it's for a DRG. Or a task could be to detect whether a patient has a particular condition from a medical record. Or it could be even narrower than that. It could be to detect whether a patient has a particular sign or a symptom, right? So those are examples of tasks. And at the task level, you can start using these foundation models as one of their inputs to be able to go build out a capability to execute the task. And that capability can then again be reused across many different scenarios. Then the layer above that is where you actually start running an actual program. So if I take a PI program, maybe you have a program to do accuracy of claim, inpatient claims from a DRG standpoint, or a program to do accuracy of claim payments for professional. And within that program, there's a set of dials that a payer wants to look for. And you want to be able to turn those dials and make sure that the solution that we put in place is reflecting in the right KPIs in the right way. So the different kinds of KPIs that you consider tracking would be things like savings, the efficiency with which the savings are achieved, the hit rates, provider satisfaction levels or upgradation levels. And ultimately, what you want is to be able to validate that as you introduce an AI intervention, those KPIs are moving in the right direction. And to the extent they're not moving in the right direction or they're not moving fast enough, we need to be able to break down why, where is the opportunity to improve, and funnel that back into teaching the AI what should be done better. So these are the layers at which, and to do all of those, you need like a key set of building blocks that we'll look at. I don't think I'm going to go through every single block here, but let me maybe focus a little bit on above the foundation models, some of the blocks that matter for making it possible to automate pretty much any task that exists in a workflow today. You can break down tasks by their nature. So you have analytical tasks and you have tasks of, I'll call it language interpretation. Historically, when people used to talk about machine learning, or as the term went in the 2020 era, we mostly were focused on automating analytical tasks. Oh, should I work on this claim or should I work on that claim? Was typically an analytical task. You could look at 100 different signals there. You could build models that could score the relative value of each claim, and you could decide, oh, you should work on this claim before you work on that. And that is still true, and it's still a critical and highly valuable place to intervene. But what's expanded our horizon is that we can now have machines do tasks that involve language interpretation as well. Whether it's reading a document to extract an insight, to extract an answer to a question, irrespective of the type of document. Could be a contract, could be a medical record, could be an itemized bill. Increasingly, we can now have task execution modules that are capable of interpreting the language and getting to an answer. And as we start building these frameworks for language interpretation, we're able to solve a wide variety of such tasks purely by configuring it to do different things in different situations. Other elements that go into it, obviously, when you have large documents, you need modules that know how to break down a document. You need modules that understand how to interpret a visual layout. All of those elements are the foundational elements that then allow us to solve a wide variety of different tasks that involve engaging or interacting with language. Another example is, okay, how do you translate language into code? Because a lot of the language that we encounter in the world of healthcare are really rules that we're supposed to follow, right? Here is, if you have a claim that involves this scenario, here is how I'm supposed to pay it. That's written down in a document somewhere. And the act of translating that into a piece of software that can actually enforce the rules, again, is a core module that is reusable across many different settings. We end up using the same modules really to be able to translate payment rules that affect how you pay a claim, as well as medical guideline documents and turning that into what should you be checking in a medical record to know whether a claim is coded appropriately. The underlying task is one of translating language into code. The specifics can vary by application. Then when you look at the highest layer of the stack, when it comes to understanding, is my program working at all? How do I know that it's doing the right thing? How do I know what I should be doing better? You end up needing, again, a core set of capabilities that cut across the specific use cases. One key thing, obviously, is KPIs. KPIs are interesting because we all have dashboards. We all have plenty of dashboards. I joke that we always have more charts than we have time to look at charts. What we focus on in the world of machine learning is that we need to have KPIs that can have a self-improvement cycle associated with them. So there is some metric that you want to improve. It's not enough to know how good it is now. What is important is to know how it's going to get better. And ideally, there would be a mechanism where you can do continuous learning. So every time the system makes a mistake, we need to know that it made a mistake, and then we need a direction to go in order to make it not make the same mistake again. So setting up infrastructure where you can continuously learn from your own mistakes is the most critical thing that we see. And that requires a lot of machinery to be able to test things, to measure things, and then to be able to simulate. Had I been smarter before, let's say you have a proposed improvement where there is a better model, being able to simulate what the better model would have done in the past, whether it would really have prevented a mistake from occurring, is very critical to knowing how you then roll out changes into production. One of the big challenges that modern AI introduces is that it's become more human-like in the sense that it's much less deterministic and reliable. So based on its mood and the time of day and whatever else, the same question might get a different answer, which makes it really critical that we have a mechanism to be able to test and verify that any change we're going to make is actually going to be making a change in the positive direction. And that requires a bunch of machinery to be able to simulate alternative futures. What if I roll this out? What would happen is a thing that we need to be able to predict ahead of time, measure ahead of time, so we can make the right changes. Obviously, there's a bunch of other technical elements here that I won't necessarily spend a lot of time on. There's a lot of security elements, PHI management, logging of enough data without really creating PHI management issues. All of those end up being infrastructure that we need to build in order to be able to maximize impact and create continuous improvement in programs. We've talked in the abstract a fair bit about all the different building blocks that are needed. So maybe I'll switch tacks a little bit and talk about an example of a program or a case study of how applying this kind of approach can result in really evolving any particular use case from one place to the other. Like I was saying, the last couple of years has been super interesting. It's probably the fastest phase shift in technology that I've encountered in my career. And the way it's manifested is that it's really helped us reimagine the art of the possible. What can be achieved with using AI relative to a world where it did not exist. This is one example where we started in the world of data mining back in 2020. Certainly our conception, the way we understood, we were new to healthcare then even. And the way the problem was described to us was really one of enforcing rules. Right? Data mining, for those who don't know, is really about taking a set of payment policies as well as contracts and making sure that claims are paid correctly according to those payment policies. It's fairly black and white in that you should be able to explain exactly how much should be paid for a claim. The provider should be able to understand that. You're not really looking at medical records or anything fuzzy to make the determination. It's quite black and white based on the claim. And on the face of it, you would think this really has nothing to do with machine learning or AI. It's really all about writing a whole lot of rules and inventing more and more rules to plug in. But as we started applying AI thinking to it, we ended up discovering that, in fact, there was material improvements we could make along a number of dimensions in growing and scaling a data mining program. And the KPIs that we were focused on involved what is the administrative cost of actually finding and fixing errors? Because traditionally, you still have stacks of vendors. And the reason we have stacks of vendors is that no one vendor is perfect at finding every single error, or no one software system is perfect at finding every single error. And we started to wonder, why is that? Why can't we just, if everybody deals with duplicate claims, so why can't we have a solution for duplicates where duplicates never exist ever again? So that is one vector where it created administrative cost and program complexity, because no solution actually would catch all the errors. A second vector was the level of automation you could apply to actually fixing errors. Historically, this has been it's a very manual heavy universe where lots of things require human intervention to figure out the right fix to apply to claims. You may be somewhat able to detect which claims are wrong to 80% accuracy, but really 80% was maybe the best case industry standard. And then the fixes were often very, very manual. So the level of automation was a big deal. And the more automated it is, the more likely it is that you could fix it ahead of time, like before the check actually goes out. So the third variable was what fraction of the errors can we stop before it occurs versus reacting to it and saying, hey, the error occurred. So over the last 4 years, as we evolved the program, as we started applying technology to the idea of, how do you capture requirements, payment policies, how do you capture contracts, how do you turn it into structured data and code that could automatically find and fix errors in as fast a cycle as possible? We've been able to show that we've been able to, first of all, grow the pie. So it ended up being the case that as you did that, you ended up more or less doubling the amount of errors that you find and fix. At the same time, we've been able to significantly increase the fraction of the errors that can truly be fixed in an automated way, where you have greater than 95% accuracy, which is pretty comparable to human accuracy when the work is being done today. So you're essentially cumulatively reducing the amount of human labor needed to solve the problem while growing the pie in terms of the total savings generated. All of this while from an implementation standpoint, we are actually significantly lowering the implementation cost of implementing a net new set of rules or constraints that CMS or any kind of standards body would publish. So that's a pretty good example of a success story. And the way we were able to achieve it hinged very, very crucially on having a feedback loop. The idea was, let's insert a solution right after the claim is coming out of prepay or whatever the case may be, where you can decide whether the claim is likely to be paid right, propose a fix. And to the extent that we did not propose the correct fix and there was a downstream process that ended up correcting the claim after the fact, how do you set up a feedback loop where you can automatically learn from that so that you're better the next day, the next week, the next month, and you can grow the set of claims that you fix before the check goes out the door? So that approach and mindset, and the program set up around it, ended up being extremely helpful in prioritizing the growth of the right KPIs in the right ways. So takeaways, this talk was mostly about operational AI. Operational AI goes above and beyond doing data science or making a toy model. It's really all about deploying it in production and then being able to measure continuously that it's doing the right thing and establishing a mechanism for how do you continuously improve it. An AI operating system is really a set of building blocks that allow you to deploy a series of AI solutions across different problems that exist in a continuum, while avoiding the need to reinvent the wheel. Increasingly, because there are so many problems that AI can solve, starting from the same data foundations, it becomes really important to invest in the right foundations so that investment can be reused to reduce the marginal cost of every net new solution that's rolled out. And in terms of what those foundations are, the key elements are the data layer itself, doing the plumbing to get the right data flowing into a centralized place where you can actually figure out the right things to do and intervene. Foundation models that essentially distill the data into deeper insights that can then help you make the right calls in a number of different areas. Autonomous task execution, so where you can take any existing workflow, you can divide it up into tasks and say, oh, which of those tasks can we delegate to AI to do well? And program optimization, where you can look at end-to-end KPIs for a program and establish a mechanism by which you can really track continuous improvement, which actually move the needle on those KPIs. And in terms of use cases where this kind of approach works, we currently are in production doing a lot of work on medical review, medical coding review, itemized bill review, data mining, as well as in coordination of benefits and subrogation. I'll stop there and open up the floor to questions. Thank you.
Thank you so much. That was an excellent presentation. We have received many great questions. Thank you to everyone who has submitted thus far. Feel free to continue adding questions as you think of them. I will do my best to combine any duplicates, and we will do our best to address as many as possible with the time we have and follow up after the webinar for any questions we didn't get to. All right, first question for you. How does the challenge of proving ROI change over the course of a new implementation? What specific metrics and stakeholders?
Can you repeat the question once more?
Sure. How does the challenge of proving ROI change over the course of a new implementation? What specific metrics and stakeholders?
Yeah, I think it really depends on the maturity of the program. So if you start from a place where there's, for a use case where there's no AI being used, the earliest types of ROI that you focus on tend to come from analytical improvements around selection of claims. So that's a common pattern. Now, obviously, the specifics can be different. But if you think about most workflows that exist, there's usually a queue of tasks to be done. And then there are two sources of value. One is, do you have the right tasks in the queue and are they prioritized in the right way? And then the next source of value is, are you able to execute the task more accurately or faster? And so the first bucket of value is usually in curating the queue itself, not so much in changing how the task is done, but curating what the task should be and how they should be organized and sorted. And it'll turn out that those are usually easier to prove out in the early days. And you can establish a baseline of value. And in general, you're always, the value from not doing a thing that wasn't necessary to do is enormous. It's 100% of time is saved, right? Versus productivity improving interventions, which tend to come second, where you're now confident you got the right tasks, they're sorted in the right order. Now you focus on, okay, can I automate some portion of the task, or can I assist a human in doing the task more accurately or faster?
All right, next question. We got an we need clean, standardized data. Like every other solution for the last 20 years, is this the point of failure?
Let me say it this way. The job gets done today, despite the data being dirty. The data is what it is. There's no magic wand that's going to make the data cleaner. Claims get paid today. They get paid after a lot of pain and a lot of back and forth or whatever, but things do get done. So in that sense, I don't think we can afford to say, oh, we need clean data before we can do anything. We have to deal with the reality that the data is dirty. Now, what we do want is to have fresh access to the data, the same data that is available within the walls, right? And what I mean by that is, if you're going to introduce AI to automate some action, but you feed it your core transactional database that maybe is attached to the mainframe, has the latest copy of the data, but then you feed the AI data that's 30 days old, or maybe it's from the data warehouse or from some stale copy, you're creating greater risk in making the wrong decision. So what is necessary, I would argue, is we must invest in creating the right connectivity to access the latest data that exists within the walls of the enterprise. But we cannot say, let's first assume that the data is clean, because then we'll never create any value.
All right, we have another question here. Please differentiate between automation and autonomy. The value of automation of manual repetitive tasks is clear, but why AI?
I tend to use the word autonomy to talk more about the modern LLM version of tasks. Historically, when we say automation, like setting aside RPA, to me, it referred to a deterministic process that you're just baking into software. Autonomy has a connotation that actually the software is responsible for doing some thinking too. It's not just about do step A and then step B and then step C. And to me, a lot of the wins actually come from that autonomy. And even with pre-LLM technology, like a lot of the administrative cost that we have today comes from the fact that the playbooks for how to do a job are not very well defined, and they don't necessarily go into the software. And a lot of the benefit comes from improving the actual playbook itself. It's not just from executing the steps. And even at the data mining case study that I provided, a lot of the improvement, the increased savings that we got was from standardizing what the playbook is, getting a robust process done for what are the right questions to ask and what are the answers, and therefore what should you do, and improving that. That resulted in greater savings because it allowed us to catch more errors.
Okay. What are the key differences in how healthcare organizations should approach experimental AI versus operational AI?
I think with experimental AI, it's all about literally speed of experimentation, or time to fail. You're not really optimizing for, is this the right long-term solution? You're really optimizing for discovering where is the opportunity. And it's really more of an exercise of, if I as a business have limited time, I can only execute so many projects, where should I invest? Should I try to solve problem X or problem Y? Let's go discover that quickly. When it comes to operationalizing AI, I think more care needs to be taken to determine the right approach. I think this is a little bit different from the SaaS world, where I think that's the extreme version where you had point solutions for everything, right? Even I don't know how many SaaS vendors we use as a company. We probably pay $10 a month per user for all kinds of little solutions, and they all work more or less independently, and it's all fine. I think in the world of AI, there is a significant force that pushes for consolidation. You want to be very thoughtful, because the same data is going to be used to solve any number of problems, and you don't want to have n different solution providers who all need the same data to do a slightly different thing, because you don't really get to economies of scale that way. So for operationalization, it's really important to standardize on the vendor. And I think the best vendor with the right operating system is going to earn the right to solve a wide variety of problems. So it's more of a platform approach.
Thank you. Can you elaborate on the frameworks needed to support operational AI at scale in a healthcare setting?
In a healthcare setting, what makes healthcare more complicated from where we sit is that many of the problems we get involved in have very well-defined and strong regulatory requirements. You cannot just use AI in the sense of, oh, I'm guessing that this is the right thing to do, so therefore let's go do it. In many situations, we are held to a higher burden of proof. If you're going to declare that a claim should be paid X dollars instead of Y dollars, you better explain exactly why that is. It's not enough to say my AI model thought that's the right answer. So there is a very important element in healthcare, which is that we need this policy framework, which explains why the decision is what it is and proves that it's compliant with the policy. Now, of course, AI can still make mistakes, and but then you'd have to trace the mistake down to say this policy requires that the answer to this question is true. We think this answer is true. Maybe our rationale for coming up with the answer is wrong. You can still trace, to the extent something goes wrong, you can trace exactly why, and can therefore take corrective action. You can say, oh, let me improve the robustness of the module that comes up with the answer to this question and plug it into a policy framework to make the final decision. That's very different from less regulated industries where you can try to do quote unquote end-to-end AI. You can just say, hey, what should I do here? And it comes up with an answer and you go do it. We can't really afford to do that in healthcare.
Okay, next question. Why is an AI operating system necessary in healthcare rather than using individual AI tools or models?
I think it comes down to the fact that there is a bunch of common componentry that ends up needing to be built, and it is reusable to solve multiple problems. I gave an example of foundation models. We take billions of claims, we build foundation models that can essentially understand the trajectory of care for patients. Now, the same model can be used for a wide variety of use cases. So if you want to do fraud, waste, and abuse, maybe you want to detect that some claim looks abnormal. Hey, we shouldn't have seen this claim for this patient. Maybe that's an important ingredient in a fraud, waste, and abuse solution. The same model can be used to detect upcoding of a claim. The same model can be used to detect anomalous evolutions in billing patterns where maybe there's a payment policy that's missing. So the same models end up producing value in lots of places. And economies of scale dictate that to the extent that somebody is investing in that layer, the cost of buying multiple solutions from the same entity would go down. So that's one force that's dictating that there is consolidation. You need a common foundation, and that common foundation is cheaper you can amortize the cost if there are multiple use cases.
All right, speaking of cost, what challenges do payers face when trying to implement AI without a centralized AI OS?
I think the challenges are that the point solutions end up doing duplicative and vaguely similar things. And at some point, it becomes unclear what the grand strategy is, what the grand vision is. If you have 15 different solutions that all try to edit a claim, how do we synergize the knowledge across all of those? How do we create a centralized view of what the features really are? Becomes harder. And in general, I would say the cost of rolling out a net new intervention gets to be pretty high. And really the game here is, assume that you will need 200 AI interventions or 500 AI interventions over a period of 1 to 2 years. How do you make sure that the cost of the net new intervention keeps going down?
All right. Lots of questions still. How does Machinify's AI OS integrate with existing systems and handle fragmented healthcare data?
That is the core of, I would say that like 70% of the effort in many ways. The AI can sometimes be the easy part, like wrangling the data is always the hard part, and that's where we need to invest, and that's where we invest. Really, it comes down to getting as deep connectivity as we can with each of our partners, with as many core systems as possible. It's not just the claims and medical records, and those are the obvious data sets that we operate with, but it's also about plugging into the contracting system to know when contracts are changing. It's about plugging into the authorization system to know how something that was authorized and the note that was typed in could influence how the claim should be paid. It's about tapping into the eligibility data and the benefits data and all of those data sets. And increasingly, we're looking at call center data. So there are all these different data sets that all provide some signal about what's the right thing to do. And the focus is to create those pipes into those data sets so we can synthesize an understanding across those data sets to make the right decisions.
Okay, I don't think this one's a duplicate. Could you explain how the policy experimentation sandbox supports continuous improvement?
Sorry, could you repeat that? I missed the beginning.
Could you explain how the policy experimentation sandbox supports continuous improvement?
Yeah, the big challenge in general, it doesn't even matter whether we're talking about AI or not, is we hypothesize a change we want to make. We want to change a payment policy, or we want to change even a model that's supporting answering a question, whatever the case may be. we want to know what the effects of the change will be before we go out and make the change. That sounds obvious, but in fact, it's really hard in healthcare most of the time. And one of the big things that the OS helps us with is how do you establish a testing framework where we can simulate the past? For example, yeah, what's a simple example I can give? Maybe let's take an example of even a contract, right? Let's say there's a provider contract. I want to make this minor change in the provider contract. I'd love to know how this would have changed my adjudication of every claim from the provider for the last 5 years. Our system allows us to go figure that out in about 5 minutes by literally reprocessing the claims under the new construct, under the new policy. The same thing holds for, what if I want to change my policy for when I declare that a patient has sepsis? So if you're tweaking some verbiage, right? So can you go back and process the last 50,000 medical records we saw where we looked at sepsis and say what would have changed? Would it have caused us to, what effects would it have had? So those simulations are really important to do ahead of time so that you know what the consequences are before you act.
All right, it looks like we have time for probably one or two more questions. How does the AI OS ensure compliance and ongoing learning in such a highly regulated industry?
I think the key to compliance is the policy framework, right? We don't want to ever have AI output being the business decision or on how to do a thing, right? The business decision emerges out of a policy framework. The AI can only really provide inputs into questions that the policy framework asks. And that's how we ensure safety. The other element of it is that there are situations or use cases where constructing the policy is the AI's job. So you can do a lot of the validation before you put it into production. Like this is true for something like payment policy. A lot of the hard work is in translating some English language payment policy document into appropriate code. So you can literally offline before you put it into production, you can have human review, you verify that in fact, it's doing what you want it to do. There is a huge testing element to it, like you test all the corner cases and say, if a claim comes like this, it should pay like that. So you establish a set of corner cases. You can prove that, in fact, it's doing the right thing and before you deploy it.
Okay, let's sneak in another one. In the case study, what specific steps helped the client reach over 70% automation in claims processing?
So to be clear, I think that's not the auto adjudication rate, which is probably like in the high 90s. So we are talking here about the really complex claims which have historically required manual touch to fix after the fact. So 70% of those fixes have been automated. The biggest thing in the early days, the biggest thing it took was we used to see, we needed to first agree on what is right. So what we found was that we as humans have a tendency to assume that just because we write down some requirements on paper and we train 1,000 people to do it, they will all do it the same way. It's actually not true. The words we use are ambiguous and different people can interpret it differently. So the first big leap was to understand why there were differences, like why did the machine and human disagree? And a lot of it came down to ambiguity and removing ambiguity from the policy. And this requires us to dig really into those corner cases, right? Not the common cases, but the extreme edge cases, and aligning on what is the right thing to do. There is a tendency in this industry to relitigate the same edge cases on a claim-by-claim basis because no one sat down to say, this is how we will handle this situation permanently, and formalized it deep enough that you can enforce it with automation. So that was, I think, the number one thing. The number two was getting deep enough integration into data so that we could truly automate. And in general, it is easier to detect problems than to fix problems. And there are many reasons why that is, which I won't get into. But once we detected the problem, it took a meaningful amount of effort to get deep integration into core systems so we could fix it.
All right, we are almost out of time. Is there any last parting words that you want to share?
No.
Awesome. Thank you again so much. You were amazing. Thank you to our audience. We are so sorry we didn't get to all of the questions, but we will follow up after. And as a reminder, a recording of this session will be available on demand within 24 hours. Have a wonderful rest of your day or evening, and we will see you all next time.
Thank you so much. Bye.